everyone. Today we will solve a few questions first, based on torque on a current carrying coil, and then we will study the last topic, moving coil galvanometer. This is the last topic of first chapter. Then another chapter will be magnetism and matter. Sundan sir, can we start now? Let's try this question, till then, everyone will join. We have a rectangular coil. Okay. We have a rectangular coil, and its length is given to be 0.1 meter, 1-2 meter, and width is given, means we can find out the area. And number of turns is 50, and it is suspended vertically in a uniform magnetic field. Field strength is given, 0.2 means B is given, N is given. We can calculate area, because the length and the width are given. The current is 2 ampere, and see if the plane of the coil is inclined at an angle, this of 30 degree with the direction of the field. The plane of the coil makes 30 degree. Then we have to find the torque. We have to find the torque. So we have formula for torque. Yesterday we studied this. Some of you might have tried this question earlier. I sent last night. And seeing one thing here, we have all data, but just note here the angle. The plane of the coil is at an angle of 30 degree with the direction of the field. Plane of coil is making 30 degree with the field. Means what about the area vector? The plane of the coil is making 30 degree, 30 degree with the magnetic field. This angle is 30 degree. Then what about the area vector, angle between the area vector? No, because in formula we have torque equal to we have mb sin theta, and magnetic moment is how much? Number of turns, Nia. If n is the number of turns, and we have b sin theta. And note this theta. This is the angle between. This is the angle between your magnetic moment and the magnetic field. And what is the direction of magnetic moment? Say just assume a current is anti-clockwise. And if we assume an anti-clockwise current, then your magnetic field will be magnetic moment will be outward, means outward normal to the plane of the coil. And if this angle is 30 degree, then this angle will be 60 degree. Means this is the direction of your magnetic moment. So theta is here 60 degree. Now everything is fine. you can put in a number of turns, and that is given to be 50. 50. We can just put that value, and number of turns is 50, current is 2, area is just length and width are given, and we can just multiply, means 0.12 and 0.1. This is your area, and field is given to be 0.2 Weber per meter square, that is Tesla, and you have to take in a sin 60. So when you get in a questions like this, just see the angle clearly, whether it is the angle between the magnetic moment and the field. And one thing more, I said yesterday or the day before yesterday that, see, if your current is anti-clockwise, then the direction of a magnetic moment is outward, no? That had a curl tool, it is outward, outward. And in this condition, while finding the direction of area factor also, we do the same thing, we call the fingers of right hand in the direction of your current, means for magnetic moment, for your area vector, and for your magnetic field. For all these three quantities, what we are doing in the case of a current carrying in a coil, we are curling the four fingers of right hand in the direction of the current, then thumb points in the direction of these quantities. So it might be clear. What is the right answer? Did you calculate? Which option? D. Yes. It's a neat question. So let's save this one. Let's move to the another slide. It's work. Just a minute. Second slide, no? Yeah. Fine. Okay. Then slide show, conference slide. Okay. Now try this question, this one. You have a current carrying loop, and it is in a magnetic field, and then you have four options here. What is the right option? Think. B, Elena, B, yes. Can be in equilibrium in two orientations. One is stable and another is unstable. You have torque equal to with M plus B, or we have torque. If you just write the magnitude, then we have T equal to MB sine theta. So when theta is 0 degree or 180 degree, theta is 0 degree, you have when theta is 0, in both conditions you have the torque is 0, but torque is 0, but when theta is 0, the equilibrium is said to be stable, and when it is in anti-parallel, M and B are anti-parallel, in that condition it is unstable equilibrium. Means if you change the angle by a little bit, the equilibrium will get disturbed. So right option is this one. This was the theoretical question. Let's move to another one. It is not working. It should work. Try this question. You have a circular coil ABCD. It carries current I and it is placed in a uniform magnetic field. If the magnetic force on the segment AB is F, magnetic force on the segment means first segment in AB, that is 1/4 of the circumference is F. Then we have to find the force. The force on the remaining segment in a BCD is how much? It is a simple question, just anything. It is based on simple concept. We started, I think day before yesterday, and we also discussed same thing yesterday, that when a current carrying loop is placed in a uniform magnetic force field, is placed in a uniform magnetic field, then F net is 0. F net force is 0. So here, if the force on this FEAB arm is FEAB, and the force on your BCDA segment, your BCDA and the remaining segment and a BCDA, then the net vector sum should be 0. So your BCDA will be how much? And a negative of, and it is given to be so minus F is the right answer. And let's save this one. And let's move to another question. Yeah, it worked now. Let's try this one. We have a triangular and a loop here. Right angled, isosceles triangle, uniform, and the magnetic force on the arm in a BC is F, then the force on the BC arm, the force is given, and we have to find the force on the AC arm. Let's try. It is a right angled isosceles triangle. Okay. Elena is right. Let's try. It is a right angle isosceles triangle. See, here also we have a current carrying and a loop. So, and a net force and will be in a zero here. And if net force will be zero, then you can write sum of forces FAB plus FBC plus FCA equal to 0. And C, it is right angled isosceles triangle. Then AC, and you have if the magnetic force on the BC arm, okay, magnetic force on the BC arm is given, BC arm is, what will be the force, what will be the force on the FAB arm here, FAB arm, can we write in this one, FAB equal to 0? Think force on an BC arm is given to be F. Force on the BC arm is given to be F. Force on this arm is given to be F. Then what will be the force on this arm? See, the angle is 90 degree. Angle is 90 degree here with the BC. So what will be the force on the FAB arm? Can we write in a 0? Because force is how much? I, L cross B. L cross B. And if the angle between length factor and the magnetic field is magnetic field is in a 0, in that condition you have a magnetic force in a magnetic force in a 0. So if FAB is 0, then how much is left? 0. FBC is F force. FCA is, we have to find out this one, and net force is 0. So our FCA force on this arm will be how much? The negative of this force. These all questions are based on the same concept, that net force, resultant force on a current carrying loop in a uniform magnetic field is 0. So let's save this one and move to the next question. Let's clear this one. Again, you have a current carrying in a loop here, and see the forces. I had sent all these equations yesterday. These all are past questions of need. Closed loop, equivarious, carrying a current. There is some current is placed in a uniform magnetic field. If the magnetic forces on the segments are given F1, F2, F3, respectively, and are in the plane of the paper along the direction shown, then we have to find the force on the segment QP. What will be the force on the segment in a QP? Anyone? Try. We have to find the force on a QP arm. If you resolve the forces there, I'm just giving the hint. Then you can find out. Suppose we have force. See, in this formula, IL cross B, this force is perpendicular to length factor, perpendicular to field, and perpendicular to the plane containing a L and B factor. So our magnetic force on this arm should be perpendicular to this PQR. So this is your F4. It is perpendicular to the PQ arm because we know the magnetic force is perpendicular to the length factor. That's why it should be perpendicular to the this arm. But we don't know the angle. We don't know the angle. Let this angle be theta. Then you can resolve this. How much will be this force and how much will be this force. This component will be F4 F4 and cos theta, and this component will be F4 and sin theta. You can solve like this also, or somebody may take this angle as theta, in that condition, but if you solve in either way, the answer should be same, because we don't know the value of the angle, If someone wants to take this angle theta, and then this component, your horizontal component, if it generally you have it this, to take angle with horizontal. Then if you take this angle as theta, then it will be F4 cos theta, and this will be F4 sin theta. And since the net force is zero, means this vertical force is balanced by this upward force is balanced by this downward force. This means this implies that this implies that this F4 and sin theta is equal to F2, must be equal to for the F net resultant force to be zero. And this horizontal force should be also balanced. Then how to balance? See, in this direction you have force in F3, and in this direction you have force in F1. Then what will be the force in this direction? We can write F3 minus F3 minus F1. F3 minus F1. And now we can simplify. Now we have to find the value of F4 force. This is the this is what vertical component, and this is horizontal component. This is horizontal component. This is vertical component. So what will be the force? You have both components. So F4 force will be what? If your vector is A here, and if this is the X component, this is Y component, then you have A equal to AX square plus AY square. You can do the same thing here. F2 square plus F3 minus F1 whole square. Okay. F3 minus F1 whole square, and F2 square. Here you have minus. So last is the correct option. It is clear? Is this clear or not? Or do you have any doubt? You can even take an angle with the particle, no problem. Generally, you have a habit of taking angle with a horizontal, and that's why I sense here. If you want, you can take this angle theta. There will be nothing, issue. Should we proceed? Elena, is it clear? Simon? Okay. Then let's move to another question. And then we have to study the last topic of this chapter. Yesterday I have sent around 10 questions, all past questions of need based on this topic. So try to solve all those and see. Another question, we have a charged particle, the charge is Q, it is moving in a circle of radius R with uniform speed V. It is similar to what we studied, magnetic moment of we wrote the symbol mu for electron, no? Magnetic moment of revolving electron. Revolving electron, we studied this. It is also the same thing. A charged particle has charge Q. It is moving in a circle, means just like orbit, having radius R. Then with uniform speed P, then how much will be the magnetic momentum? If you remember, then fine. We added a derived node, this one QVR by 2 or EVR by 2, EVR by 2. And if you forget, and then it's simple. See, magnetic moment is how much? Current times area. Area will be pi r square. This current will be, let's take the time interval as one time period. Charge by time, area, Q, and time period you have, distance covered in one time period is 2 pi r by V, and your area is pi r square. See, one cancel, pi cancel. If you forget, and then you can calculate like this. V will go upward, then it will be QVR by 2. Is it clear? It is a very simple question. So I think I saved this one. I am just starting a new session because it will stop in the middle, and then we'll start a new topic. Okay, let's start new session.